Once we explain the proof of the master's theorem, that how the cost of recursion is contributed either by the root level or the leaf level, let's formulate them here. So it applies to the same particular family of recurrence of the form Tn equal to a times Tn by b plus Fn, where a is greater than equal to 1 and b is greater than 1 and Fn is asymptotically positive, which I've already said. So now compare Fn with n to the power log a to the base b. Now if you remember what Fn was the non-recursive part, okay, so this part which is actually going to the root, it's like the combination for the divide and conquer algorithm, and n to the power log a to the base b, if you remember, this was the number of leaf nodes at the lowest level, okay, so it was like a to the power h. So then h was log n to the base b, and then we shifted the base base change of logarithm, and it becomes n to the power log a to the base b. These are the number of leaves, and this is the root, okay, root and leaf. So when we say compare Fn with n to the power log a to the base b, we are trying to compare the cost which is incurred by the root level with the cost that is incurred by the leaf level. So now, as we said, there are three different cases. The case 1, Fn equal to big O of n to the power log a to the base b minus epsilon for some epsilon greater than 0. Okay, so here, what does it mean? It means that function of n is polynomially smaller than n to the power log a to the base b. That means the leaf level is contributing more than the root level, okay. So the root level Fn is upper bounded by the leaf level's cost. So leaf level's cost is higher and it's also bounded by a polynomial factor. It's a polynomial time smaller than the leaf level. Root level is polynomial time smaller than the leaf level. So in that case, for this case, case 1, Tn will be written as theta of n to the power log a to the base b. That means since leaf level is the upper bound, then leaf level is the asymptotic cost, okay. So whichever, as you know that for asymptotic cost, as whichever is the contributing more, that is the deciding cost factor, okay. So now let's consider the case 2, where we said that every level is contributing equal. So in that case, we actually multiply the cost of individual level with the height of the tree. Okay, now this is a little bit tricky way of writing this. We say that Fn is equal to theta of, with some constant factor, this bound from top and bottom by n to the power log a to the base b log to the power kn. Okay, so this logarithmic function is called polylogarithmic function. Okay, so for some k greater than equal to 0, it can be equal to 0. So that means there is no log factor. That's perfectly possible. So when you see that it's just in some textbooks, some online materials, you might see that it's theta of n to the power log a to the base b. There is no log factor. So, but this is a better way of representing, because in some cases there can be a log factor. In that case, what happens is that Tn is theta of n to the power log a to the base b multiplied by log to the power k plus 1n. Okay, so that means one extra log factor comes in. Now for merge sort, we have seen there was 2Tn by 2 plus theta n, and because every level contributes same amount of cost, so we added a log factor, which was basically because of the height of the tree. Here also, it's actually we are doing the same thing, and we are saying that the interpretation is that we add an extra log factor. You see, the k becomes k plus 1. So if k equals 0 originally, then it becomes 0 plus 1, that is 1. That is one log factor comes in. And if there is a k equal to 1 here, then it will be 1 plus 1 to log square n. Okay, so it's up to a polylogarithmic difference between the root and the leaf. So it's not a polynomial difference, just a polylogarithmic, a very, very slow difference. That means their growth rate is within a constant factor of each other. That's why it's theta, okay? Remember it. So now Fn equal to big omega, the case 3, Fn equal to big omega n to the power log a to the base b plus epsilon. What does it mean? Big omega means this is the lower bound. So Fn is being bounded from the bottom by the leaf's cost. So Fn is higher than the leaves cost. How much higher? Up to a polynomial factor higher, okay, where epsilon greater than 0. And there is a regularity condition. Let me explain it right after telling this. So here, if in this case where root is the contributing cost, then root will be the asymptotic cost of the recurrence. Okay, so that's the same way Tn equal to theta of Fn. That means root is the contributing cost here. So you see case 1, leaf was the contributing cost. So leaf was the cost here in the final cost in the asymptotic analysis. In case 3, root is the contributing cost. And so the final cost of asymptotic analysis of the recurrence relation is the root's cost. And when the root and leaf are within constant factor of each other, logarithmic, polylogarithmic factor, then we give the cost of the either of the cost. Here we consider the leaf's cost and with a logarithmic factor. Okay, so extra logarithmic factor. Now I hope you understood. This is called a regularity condition. Okay, so this is actually trying to check that, okay, when you go down the tree, this level and then in this level, we are trying to show that this level is less than the cost at this level. That means it's decreasing, the cost is decreasing. Okay, so this is the checking here. So that the cost as a function of n is higher than the cost at this level. This is actually a times f of n by b, and this is the cost of, the root, suppose fn, and this is a times f of n by b, has to be less than the cost at the root level. So that means it's a decreasing cost. So that means it's a case 3. So we do not always check the regularity condition, but whenever we have, it might have some difficulty, so let's check the regularity condition, and then we check the regularity condition. In most of the cases we should technically check, but sometimes we straight away know, oh, this is case 3, then we do not really need to check. But I'm not saying that it's a good idea to not check, but I'm saying when you see straight away, okay, it can be done, you can omit it, but in the exam or other places, I would like you to show this thing. Let's see some examples, okay, now, so that we get a basic idea of how the thing is working on. Very simple Master's theorem. So Tn equal to 4Tn by 2 plus n. This is a recurrence relation I have given you to solve with the Master's theorem. First, you have to find out what case it is, and then only you can give the final solution. It has to be one of the 3 cases, but there are some recurrence relation which does not fall in this kind of formulation. Okay, so like this, all the criteria has to be met. If it does not meet those criteria, then we say that the master method does not apply, and using master method we cannot solve this recurrence relation. Let's see this one. So here 4Tn by 2 plus n, we can even write theta of n. Okay, so sometimes it can come as theta of n, sometimes it comes as n. So do not do not get confused. So in that case, we have to identify which is a. So this is a. So I have written here a equal to 4. Okay, so this is b. So I write here b equal to 2, and this is fn. Okay, so the non-recursive part. So fn equal to n. So okay. So now what we have to do, we have to compare fn with n to the power log a to the base b. If you remember, that was the number of leaf nodes. So n to the power log a to the base b is what? N to the power, we just put the values, log 4 to the base 2, which is n squared. Okay, now we see n squared and fn, we compare. Okay, so fn equal to n squared minus 1. Okay, equal to n, because fn is n. So n squared minus 1 means n squared minus epsilon, where epsilon equal to 1. Okay, so epsilon, if you remember, this is the epsilon. So the leaf level is growing faster by a polynomial factor, and that's why leaf level should be the the final result following the case 1. So we have to first write n squared is bigger than fn by a polynomial factor. So that implies this is in the case 1 of Master's theorem. And what will be the solution? Tn equal to theta of n to the power log a to the base b, which is theta of n squared. Okay, so I directly wrote it. I should have written Tn equal to theta of n to the power log a to the base b equal to theta of n square. I hope you understood why this is case 1. Now let's consider another solution. Here I didn't solve it so that I can solve it in the camera. So Tn equal to 4Tn by 2 plus n cube. So here a equal to 4, b equal to 2. So n to the power log a to the base b equal to n square. Same as in here, okay? So here also we have shown similarly. Now Fn equal to what? Fn equal to n cube. You see, I have shown the same problems using the recursion tree. Okay, now I'm showing them using master method. Fn equal to n cube and n to the power log a to the base b n square. When we compare them, we find that Fn is larger. Okay, so you can see Fn equal to n square plus e, where e equal to 1. Okay, so this is C, this is in this case. Okay, n to the power log e to the base plus epsilon. So that means this is case 3. So this is case 3. When we say something is case 3, we should show the regularity condition. How we can show the regularity condition? A equal to 4. So let's see, 4 times function of n by b, which is function of here, function of n in space of n, we put n by b, which is n by b equal to 2, n by 2 whole cube. Is it less than equal to 1 minus epsilon prime fn, where fn is n cube? So let's see, it's 4 times n cube 8, so it's cancelling, less than equal to 1 minus epsilon prime n cube is n cube by 2. So is it possible if epsilon prime greater than half? So this is n cube by 2 less than equal to 1 minus epsilon prime n cube. Is it possible? Yeah, it is possible as long as epsilon prime is greater than 0.5. Okay, greater than equal to 0.5, we can say. That means this regularity condition holds. You see, greater than equal to 0.5 or less than equal to 0.5. I think it's less than equal to 0.5, right? Because it's subtracting 0.5 greater than 0. Greater than epsilon prime is greater than 0, so it's greater than 0, less than equal to 0.5. Okay, so less than 0.5 will be better. So we can find some value of epsilon prime. That's the basic idea. That means regularity condition holds. So that is, this is case 3. If it's case 3, what is the solution? The solution is Tn equal to theta of Fn. So Tn equal to theta of Fn, that is theta of n cube. Okay, so that means this also is solved. Now let's try to solve this problem, which is here, and let's show how it works. This is a equal to 4, b equal to 2, fn equal to n square. Okay, so n to the power log a to the base b equal to n square, as we have already calculated before. Okay, so now what we do, we compare n square with fn, and we find fn is also n square. So their growth rate is same. If their growth rate is same, then we can represent it like this. Okay, n square log multiplied by log to the power 0 n. Okay, this one fn equal to fn is n square. So n square equal to n square log to the power 0. So that means the solution will be Tn equal to theta of n to the power log a to the base b, which is n square log n. 0 plus 1, that is 0 plus 1, that is 1. So that is n square log n. That's the solution. Okay, theta of n square log n, and this is case 2 because the growth rates are same. Okay, so n square equal to n square multiplied by log to the power 0 n. So this is case 2. So I've shown you what is Master's theorem, and I've shown you 3 different examples of case 1, case 2, and case 3. And there'll be a lot of problems in the worksheet which you can solve to increase your understanding and see more examples in different places, in the internet or in the book, and it will clarify your concept.